All right, welcome to Mr. B's Biology. We're going to be talking about carbon dioxide transportation today. So carbon dioxide, about 200 milliliters per minute, carbon dioxide is generated through various processes in these cells, such as cellular respiration. And we have to transport this carbon dioxide to the lungs so that it can be expired or exhaled back out into the environment. So there's a couple ways by which we're going to transport this carbon dioxide via blood. So the first thing is carbon dioxide just simply diffuses into the blood plasma. Here it'll become carbonic acid, H2CO3, or it can be bound to plasma proteins to form carb-amino-protein complexes. Carbon dioxide is also going to enter the red blood cell, and here it essentially goes through two transportations, two modes. So one is it's going to bind directly to hemoglobin, and the majority, about 70%, is actually going to go through a conversion process under the influence of this enzyme carbonic anhydrase. So carbon dioxide with water forms carbonic acid. So carbonic acid is formed in other ways. So ocean acidification, if you've heard of this unfortunate phenomenon, what's occurring is the carbon dioxide in the atmosphere, especially as carbon dioxide is accumulating in the atmosphere, when it makes contact with, for example, the ocean water, it's going to diffuse in that water, and it's going to form this association, this carbonic acid with water. So carbon dioxide plus water makes carbonic acid. And of course, if you're a marine life that makes something like a calcium carbonate structure, an exoskeleton, then this is going to impact you. It's going to cause issues with the formation of this calcium carbonate. And therefore, there's problems, obviously, with the bleaching of coral reefs. This is the phenomenon that's occurring because of the increased acidity via diffusion of carbon dioxide in water and the formation of carbonic acid. But here in the red blood cells, we actually want this to happen. So what we're going to do is we're actually going to speed up this reaction via carbonic anhydrase, and we're going to get carbon dioxide plus water, making carbonic acid, and then that's going to dissociate into hydrogen ions and bicarbonate ions. So the first thing to talk about is what do we do with these hydrogen ions? So these hydrogen ions are actually going to bind to hemoglobin. So that's one thing we can do. By binding them to hemoglobin, we essentially put them on something. So that helps to neutralize them, helps to keep them inactive. The other thing we're going to do with the bicarbonate ions, so we can do a couple of things here. One, bicarbonate ions are just going to diffuse out of the red blood cell into the plasma. But in this process, what's going to occur is we're actually going to get chloride moving in. Because we're losing the bicarbonate ions, which are also anions, and we can see chloride are obviously anions as well, this could cause issues, especially related to osmosis. So the chloride shift is the movement of chloride ions into the red blood cell because bicarbonate ions are going to leave the red blood cell. So this helps maintain osmotic pressure within the red blood cell. Now these bicarbonate ions, again, they're going to go through two processes. One, they may form carbonic acid. But two, a lot of them are actually going to look for sodium ions, and that's going to form sodium bicarbonate. All right, so NaHCO3. All right, so sodium obviously is a cation. Bicarbonate, these are anions. They want to form that ionic bond. They want to form that ionic relationship, and they will. So we get sodium bicarbonate, this wonderful buffer. Now, when we get to the alveoli, we're going to see essentially the reverse of what we just talked about. So I'm going to come in here. So we have carbon dioxide, which became carbonic acid. We'll go through this process of dissociating so that we get CO2 plus water. And now that CO2 is free to go into the alveoli. So it's going to diffuse out of plasma. It's going to cross the thin basement layer. It's going to cross the endothelial layer of the pulmonary capillaries and enter the alveoli. Okay. Sodium bicarbonate ions, so that will dissociate as well. So now we have the bicarbonate ions that want to enter the red blood cell, and that means the chloride are going to leave. And we'll talk about the fate of those bicarbonate ions in a second. The other thing to mention too, we have the carbino-protein complexes. So the carbon dioxide associated with these plasma proteins are going to also dissociate so that it can become free carbon dioxide, and therefore it can also diffuse from the plasma into the alveoli. All right, so the bicarbonate ions that enter the red blood cell, so we're going to have dissociation of the hydrogen ions from the hemoglobin. So we got these bicarbonate ions that are entering in. So as we can see, when we combine these two, we can reverse the reaction that we talked about before. So with carbonic anhydrase again, we can take the bicarbonate ions that have come in, especially the ones associated with the sodium bicarbonate that had left the cell previously. Those enter the red blood cell. The hydrogen ions dissociate from hemoglobin. And now, under the influence of carbonic anhydrase, we can reverse this reaction. We can get carbonic acid formation, and then that will dissociate into water and carbon dioxide. And now that carbon dioxide is free to leave the red blood cell and travel to the alveoli. And of course, the chloride are going to be shifting because we no longer need them in here because the bicarbonate ions are coming in, so the chloride ions are going to go back out into blood plasma. So that is how we unload carbon dioxide from the various processes that were involved with inside the red blood cell, and then of course the carbon dioxide that was traveling plasma by either being bound to the plasma proteins via the carb-amino complexes or as carbonic acid. All right. So what happens when we get disruption with the normal rate of carbon dioxide? So we're going to talk about some issues that can arise here. So the first one is hyperventilation. And then the second one is going to be hypoventilation. And keep this equation in mind because we're going to be discussing this. We just talked about this where we get carbon dioxide makes carbonic acid, makes bicarbonate ions and hydrogen ions. So this is an important equation to know. Let's talk about hyperventilation first. So what happens with hyperventilation? If you think about hyperventilation, the first thing you should think about is you have an increased respiration, particularly exhalation. You're panicking, you're having a panic attack, or something else is causing you to breathe out too much. And by breathing out too much, you're losing too much carbon dioxide. You're breathing out too much carbon dioxide. So we get an increase in the exhaled carbon dioxide, and as a consequence, we're going to get excessive loss of carbon dioxide. And my rough graph is representing that. So if we think about, we have partial pressure of carbon dioxide on the x-axis, and we have the ventilation, on the y-axis, and we have ventilation on the x-axis here, then we could see that we see a steep drop in the partial pressure of carbon dioxide with increased ventilation over a course of time. And that's not good because we get excessive loss of carbon dioxide, and the consequence of that is we're going to see an increase in blood pH. All right, so we think about carbonic acid formation. We have the hydrogen ions and the bicarbonate ions. If we're losing too much of that, because there's a balance to this, if we're losing too much carbon dioxide, therefore we're going to see carbonic acid levels dropping. And because this is involved with the overall pH, although obviously it's slightly basic when we're talking about blood, it's about 7.4, obviously it's a small range. We're going to see less carbon dioxide because of the increased loss of carbon dioxide in blood. We're going to see less carbonic acid, and therefore we're going to see an increase in blood pH. We're going to be becoming more alkaline. All right, so this leads to respiratory alkalosis. Now we can talk about the opposite effect. So if we have hypoventilation, for example, if somebody has chronic obstructive pulmonary disease, they're breathing out slowly, they're having difficulty ventilating and especially breathing out. So decreased respiration with something like chronic obstructive pulmonary disease, COPD, what we can see is actually less carbon dioxide that is being exhaled because ventilation is being disruptive. We have lower respiration rate. This is going to lead to accumulation of carbon dioxide in tissues. Ultimately, we're going to see a drop in blood pH. We're going to become more acidic because there's going to be more carbon dioxide in the tissue fluids, in the blood plasma, in these red blood cells. So that's going to lead to more carbonic acid, more hydrogen ions and bicarbonate ions, and that's going to lead to a drop in blood pH. And this is referred to as respiratory acidosis. Now, how does this work regarding this equation? So let me get some colors here. Colors are always helpful. All right, let's get to our blue. We're going to start with talking about hyperventilation. So again, if we're hyperventilating, we're losing too much carbon dioxide. So how would this work? What would we expect? So we're increasing the amount of carbon dioxide that's lost, and therefore we're going to have that problem of seeing less carbon dioxide in our blood, increase in blood plasma, and therefore we're going to see this equation being driven more towards the left. All right? Because we're going to have less carbon dioxide, less bicarbonate ions and hydrogen ions, and more CO2, especially being breathed out via ventilation. I'm just going to say vent. All right, then what about hypoventilation? So hypoventilation is going to be the opposite. So if we're talking about hypoventilation, we're obviously less carbon dioxide that is being breathed out. So therefore, there's more carbon dioxide that's in our tissue fluids, that's in our plasma. So we're going to see this equation being driven more towards the right. We're going to have more carbon dioxide and water becoming carbonic acid to becoming hydrogen ions and bicarbonate ions. So it's going to drive this equation more towards the right. And these are questions I like to ask on exams. I imagine professors, other professors that teach anatomy and physiology also like to talk about these things as well, because this is important. Because again, respiratory alkalosis or respiratory acidosis, this is what we're expecting. This is what we see. We see issues regarding the exhalation of carbon dioxide. What is causing either too much of it lost through something like hyperventilation, or what is causing not enough in this case. So too much carbon dioxide accumulating in these fluids, such as in the tissues or in the blood plasma. And again, respiratory alkalosis, it could be somebody having a panic attack. It could be associated with fever. Sometimes people hyperventilate when they're having fevers. Hypoventilation, anything that's obstructing the breathing, such as chronic obstructive pulmonary disease, asthma, etc. These could all cause issues with increased carbon dioxide. And it's worth noting that when we talk about metabolic acidosis or alkalosis, the respiratory system is often matching the issues here. So you could have increased respiration rate or decreased respiration rate as it relates to whether somebody has metabolic acidosis or metabolic alkalosis. So we get these different compensatory mechanisms that are involved, whether it's respiratory, renal, or via this carbonic acid bicarbonate system, this buffering system that's also involved with this. And I will obviously make videos discussing all that at some point, because that's also important to know, especially for clinical reasons. All right, well, thank you very much. Hope you found this useful, and talk to everybody soon. Bye-bye.